to talk about the main events of the cardiac cycle. The main events of the cardiac cycle. Now, where can I find this PowerPoint? This is still Human Cardiovascular System 2, which is on Teams. Okay? And now we're talking about slides, I think, roughly between 54 and 69. So the major big PowerPoint on Teams called the Human Cardiovascular System, slides 54 to 69, and your opening slide should look like this, so you know where you are. Okay. Let's have a recap. We already kind of know that the heart is everybody's saying for me at home, don't be self-conscious, even though the neighbours might be thinking something's going horribly wrong. Pump. The heart is a pump. How many chambers has it got? How many? How many? 4. It has 4 chambers. And we already know that it's got pipes, which we call arteries, and veins, which are kind of going out and also coming back in. Arteries always taking things away from the heart, and veins always bringing it back to the heart. Well, we now know that the heart is said to be myogenic, which basically means it beats on its own. It can beat on its own. This time what we're going to do is we're going to look at the movement of the heart during one cardiac cycle. Okay? We're going to look at the movement of the heart during one cardiac cycle. So if your heart beats once every second, okay, which is roughly what it might be doing at rest right now, then realistically this is happening 60 times in a minute. So what I'm about to describe for you now is happening inside you once every second. It's going to take me slightly longer than a second to tell you, but it's happening once every second. Good. Everybody all right? Brilliant. Now there's a lot of writing on these slides, so you can going to go through it with you, but you do kind of need to look at the PowerPoint as well. Now, just as always, try to make this as easy as I can for you. Okay, don't tell anybody else. But all the important stuff is in red. Okay, all the important stuff is in red. So for me, for your assignment, what you're going to be thinking about creating is, can you show me that you understand each stage of the cardiac cycle? What are the critical things you would want to tell me about the cardiac cycle? Showing me that you understand what is happening in each part of the cardiac cycle. Now, the cardiac cycle in nature is a continuous thing. But to make it easier for students and to make it easier for me, we kind of break it down into various little components that we call phases of the cardiac cycle. So don't think of these as completely separate little things. It's part of a seamless thing that is happening in your heart, in one heartbeat. Okay. So, let's have a look at this PowerPoint together. Let's have a look at this as we go through. We're starting our journey in the heart. We are particularly concerned at this point about what is happening in the chambers at the top of your heart. They begin with an A, they're called atria. So phase 1 of a heartbeat, 1 every second, 60 every minute, is going to start in the atria, phase 1. So what are the important features of phase 1, Dave? Well, if you give me a minute, I'll tell you. Okay, all right. Tell me, surprise me, what the hell is happening in phase 1? Wait, okay, so your AV valves are open. Remembering that these are the valves between the atria and the ventricles at this particular stage. The AV valves are open. Very often, we regard this as the first phase of the cardiac cycle. And when we look at ECGs, and you will have a little lesson on ECGs, this is the same as the P wave on your ECG. Okay? The depolarization, the electrical current moving through the atria, getting those atria to contract. Okay? So whenever we see that word depolarization, I want you to think of electricity that is moving, which is causing the heart muscle to contract. Boom. So what you're going to get is that this initial movement of electricity through the atria is going to get the atria to contract. What do you think is going to happen? Thought about it? Well, blood from the atria is going to get forced through the open AV valves into the ventricles at the bottom. And we refer to this as atrial diastole. Whenever you see that word diastole, you just think squeeze. Spelled wrong. But hey, squeeze, okay? You're thinking of a squeezing. So the atria are now going to squeeze. They're going to force blood from the top of the heart through the open AV valves into the ventricles at the bottom. How does it do this? Well, when they squeeze, the pressure in the atria increases. They squeeze, the pressure increases, and it forces the blood all the way through those open AV valves into the ventricles at the bottom. Squeeze at the top, blood shoots through the open AV valves and arrives in the ventricles at the bottom. Now, we'll kind of see the significance of this. Because your atria only really empty round about 30% of the total blood volume with an atrial contraction. Because those AV valves have been open all the time and blood has been returning to the heart on the left and right hand side all the time, blood has simply just flown through the open AV valves into the ventricles at the bottom. This first phase squeezes round about the last 10 to 30% of the blood from the atria into the ventricles, which kind of means, as we'll see later on, if this part of the process goes wrong, you're not really going to die because you've still got round about 70% of the blood already in your ventricles, okay? But the patient will feel very, very different if the atria aren't working correctly, okay? So, just as a quick recap, AV valves are open between the atria and the ventricles. Okay? Blood is passively by gravity falling through from the atria into the ventricles. The first time your sinoatrial node kicks in, it's going to send an electrical current out through the atria, getting the atria to squeeze. The pressure in the atria goes up, which means that the remaining blood gets forced through, round about 10 to 30%. Phase 1, a lot of writing, a lot to take in, have a look at the PowerPoint. Is everybody okay? Okay, let's look at phase 2. Before we do so, silly mistake from Dave, here is our first diagram. Here is the blood on this side, which of course is blue, because it's coming back into the heart, flowing through the open AV valve. Can you see it here? AV valve, open, flowing through this side, through the AV valve. This time, of course, it is oxygenated, which means it is red. Okay? So here we are, AV valve is open, flowing right the way through. You can also see on this particular slide that we've got two other valves that we're already kind of aware of. One is on the PA, which of course is the pulmonary artery, which we now know takes blood to the lungs. And on this side, we have got a large blood vessel coming out here. Begins with A. It is an artery, but we call it the aorta. And that is taking blood right the way around the body. And you will notice that there are valves here. These are called, if you remember, these are called semi-lunar valves. These are called semi-lunar valves. They are smaller than the AV valves, much smaller than the AV valves. And if you look at this diagram, can you tell me, are they open or are they closed? Are they open or are they closed? Had a think about it? They're closed. Can you see here that they are closed? This one is closed, and this one is closed. The AV valves are open, the semilunar valves are closed. Okay? Let me just add something to this, just so it kind of contextualizes where we're going with this. This valve is closed and is held closed by the amount of blood that's actually sat above that valve. So this pipe here, the pulmonary artery, is full of deoxygenated blood. Because the ventricle isn't contracting, that blood isn't moving anywhere just yet. On this side, the aorta is full of oxygenated blood. But again, because the left ventricle isn't contracting at the moment, this weight of blood keeps that valve closed. This weight of blood keeps that valve closed. Okay. Just store that away, because that will become significant slightly later. Okay, let's now look at phase 2. All of a sudden things are starting to happen. Okay, major things are going to start happening now. All of a sudden, big change, everybody. Now all the valves in the heart are closed. This is the start of what we will see in the ECG as what we call the QRS complex of the ECG. What does that mean? What does that mean? It kind of means that the ventricles are starting to squeeze. They're starting to squeeze. And whenever they start to squeeze, it means the pressure in those ventricles is going to go, is it going to go up or is it going to go down? If it squeezes, is the pressure going to go up or is it going to go down? Have a think about it. It's going to go up. When the pressure starts to go up, those ventricles are squeezing. So just remember that. When we're starting to squeeze, pressure goes up. So now in phase 2, what we're talking about is the contraction of the ventricles. We've now got that electrical signal, remember that word depolarization, which means that electricity is causing the muscle in the ventricles to contract. Okay? Everybody happy with that so far? We call this ventricular diastole. Ventricular diastole. Diastole means, we said it before, diastole means squeezing. Squeezing. Now, what then happens is, what you're probably thinking is, what the hell has closed the AV valves, Dave? What's closed the AV valves? What has forced the AV valves to shut? Previously, they were open and blood was flowing from the atria into the ventricles. But now, the pressure in the ventricles has started to go up because they are squeezing. You're now going to force blood back towards the atria. But this time, we don't want the blood to go back into the atria because valves only allow blood to flow one way. So we don't want blood going back into the atria. That pressure of the blood in the ventricles is now squeezing, and its natural direction is to force it back the way it came in, because that's the easiest way for it to go. But the AV valves basically get forced, pushed, closed as the blood basically rushes back towards the atria. It literally forces them closed. Bang! And we all now know that our first heart sound that we can listen to, which is low, okay, is made by those AV valves slamming closed. So the AV valves close when what we call the inside ventricular ventricle pressure exceeds the pressure of blood in the atria. There's hardly any pressure in the atria because all the blood's gone through. So now when the ventricles squeeze, the pressure's going to want to force it back into the atria, back into this hollow area, but it won't go that way because that pressure closes the doors and slams them shut. It closes the AV valves, slamming them shut. Now some of you are probably thinking, hang on Dave, that's an awful lot of pressure on that valve. and that valve is kind of very delicate. What stops the valve blowing open and allowing the blood to go back into the atrium? Well, when the ventricle starts to contract, it also triggers contraction of what we call the papillary muscle. The papillary muscle is on the walls of the atria, and attached to the papillary muscle are cords. You can kind of think of them as parachute cords. And these parachute cords are attached to the AV valves. So when the pressure down here goes up and the ventricle squeezes, this papillary muscle pulls on those cords to stop the valve from blowing open the wrong way. And that's what it does. It's great. When those cords go wrong, or when those valves go wrong, then we do get something which is called regurgitation. The valve opens and blood goes back into the atrium where we do not want it to go. And we kind of have to fix that. Anyway, that closure of the AV valves results in the first heart sound, which is, did everybody say it at home? Low, the first heart sound. So now, all of a sudden, we've got all the valves closed. The pressure in the ventricles is going through the roof, but there's no change in the volume. The volume of blood that's gone in remains the same, but the ventricles are squeezing and squeezing and squeezing, but there's no change in volume, which is why we call it isovolumetric. In other words, pressure in the ventricles is going up, but there's no change in the volume in the ventricles. So we've got this massive increase in pressure, but with no change in the volume. And that pressure is rising and rising and rising. So let's have a look at that on the diagram. Here we are. The pressure in both the left and the right ventricle is going through the roof. Remember, we have still got a load of stationary blood, basically, which is in here. And we've got a load of stationary blood, which is in here. In the pulmonary artery and in the aorta. So these basically are weighing down on this valve. There is a weight of blood weighing down on these semilunar valves, holding them closed. The pressure in here has forced these valves, the AV valves, closed. I'll just use a green pen. What is holding them now closed against that pressure is the papillary muscle, which is attached to the wall down here of the actual ventricle, and there are cords which run up to the valves that basically stop that valve from doing what we don't want it to do. We do not want that valve to open that way, because that would allow all of the blood that is down here, which should be in blue, all the blood which is down here, to go back that way. It's only just come in. We don't want it to go back into the atria, because valves only allow blood to flow in one direction, and the direction they allow blood to flow in is that way, not that way. Okay. So now we've got this massive build-up of pressure, no change in volume. So the next one, you're probably thinking, this is going to basically erupt. Something has got to give. Something's got to give. Now all of a sudden we get this explosive release of blood from both ventricles. The pressure has increased massively. And now all of a sudden, for the first time, our aortic and our pulmonary semilunar valves open. What forces them open is the pressure of blood which is in the ventricles. Our AV valves between the atria and the ventricles remain closed to stop backflow. This is basically the ventricles continuing now to squeeze. This is when you see that massive, rapid ejection of blood into the aorta and into the pulmonary arteries from the left and right ventricle, respectively. Why does it happen? Why does that happen? Because the pressure of blood in the ventricles is greater than the weight of blood holding the semilunar valves closed. When the pressure of blood in the ventricles is greater than the weight of blood holding the semilunar valves closed, it effectively means the semilunar valves are forced open. Now all of a sudden, we've got blood moving out of the heart into the aorta, and we've got blood moving out of the heart into the pulmonary artery. So those valves are now open, and blood is now moving to the lungs, and blood is now moving right the way around the body. So our diagram looks like this. The pressure in here is now so high that it has forced this valve open, meaning the pressure in here is greater than the weight of blood that was previously holding it closed. Boom! This has squeezed so much that all the blood from here is now being ejected into that pipe, because the pressure in here is greater than the weight of blood holding that valve closed. And it's true for the other side of the heart as well. This particular ventricle, the pressure here is so great that it has overcome the weight of blood that is above the valve here, and it has forced that valve open, and blood is now actively moving to the lungs, and is now actively moving right the way around your body. Boom, boom. Now, because this is a continuous cycle, we kind of move now into what we call phase 4, reduced ejection. If that is basically the lid coming off the volcano, the previous one, now we're kind of talking about the volcano starting to die down a little bit. However, the pressure in the ventricles is still sufficiently high to keep the aortic and pulmonary valves open. It is still high enough to keep the AV valves closed. But now the ventricles are starting to relax. Okay? So what we're talking about is the residual end of that pressure. The ventricles are now starting to relax a little bit. Okay? Hence we call it ventricular diastole. Diastole just means relax. The ventricles are now starting to relax. Okay? So we've moved past the QRS component of the ECG, and now we're into the relaxation phase, which is on an ECG, the T wave, as we'll see in a later lesson. So this is equivalent to T wave on the ECG. Whenever you see that word depolarization, I said that electricity was moving, which made the heart squeeze. Okay? Depolarization makes the heart muscle contract and squeeze. Whenever we see this word repolarization, I want you to think of the word relax. Because the heart muscle is relaxing when the electrical signal is repolarizing. In other words, it's kind of recharging itself now, ready for the next time it needs to beat. Okay, and so our diagram looks like this. The pressure now is starting to fall. The pressure is starting to fall because these walls are now starting to relax. But the pressure is still high enough to force blood out through the pulmonary artery, and it's still high enough to force it out through the aorta. It is still high enough to keep the AV valves closed. It is still high enough to force blood through these, because the pressure here is still just about greater than the weight of blood that we've got in both of these pipes. But instead of the flow being massive out of these pipes, the pulmonary artery and the aorta, it's now kind of slowing down. Whereas before, it was kind of boom, pressure, boom, massive pressure, massive ejection, wallop. Now it's kind of like a tap that doesn't quite turn on. It's kind of just dribbling its way out a little bit. Beautiful. Phase 5. Now we're into full relaxation. The ventricles are now relaxing. The pressure in the ventricles has now completely dropped, which means for the first time there is no longer sufficient pressure to keep the AV valves closed, which means now the AV valves open. Okay. So now we're into phase 5. We've had this massive ejection, we've had a reduced ejection of blood, now we're getting into relaxation. Isovolumetric relaxation. All valves are now closed because the pressure in the ventricles is so low that basically we're now into what we call ventricular diastole, which means all these valves are shut, everything is closed, but now all of a sudden, when that intraventricular pressure falls sufficiently, what we now have is both the aortic and the pulmonary valves will now basically abruptly close, which gives our second heart sound, which is do. Okay? AV valves are still closed, but basically now what we get is the closure of the semilunar valves. Okay? So in our diagram, AV valves still remain closed, but the pressure in here now has dropped sufficiently, so the pressure in here is less than the weight of blood above it, which wants to come back through gravity. And also, because these are expanding, it's almost like a suction pump, it wants to pull blood that way. But now the blood can't come back that way because this valve now slams closed, and that semilunar valve also slams closed, which means we get our second heart sound, which is do. Sound 2. Do. So all valves are still now closed. These two have just made that second heart sound, which is do. And now we're kind of almost at the end of one cardiac cycle. All of a sudden now we're up to phase 6, where we get rapid refilling of the heart. For the first time in a long time, our AV valves are now open, which means that the pressure in the ventricles is so low that the pressure above it in the atria of the blood that's been returning all the way through the cycle, through the aorta, through the pulmonary vein, and also through the vena cava, the pressure of blood above it is now sufficient to force open the valves. So for the first time in a long time, the AV valves are now going to open. And they're going to rapidly open, and blood is basically going to flow through gravity, and nothing but gravity is going to flow back into your ventricles. Normally, ventricular filling is silent, is absolutely silent. So let's just look at that on our diagram. First time in a long time, blood is now going to flow back this way, all the way into here. This valve, for the first time in a long time, is now open. Why is it open? Because the pressure in here is so low that the weight of blood that's been returning all the way through the cycle, I'll kind of draw it like this, here is blood that's been returning all the time as the ventricles have been forcing blood out through the pipes. The weight of blood in here is now greater than the pressure here, so it forces the valve open and blood simply pools through. So now all of a sudden blood will end up down here. Not because of anything contracting, but simply by gravity alone. And the same thing is happening on this side as well. Blood's been coming back into this atria all the time the other cycles were going on. But now, the weight of blood that was up here has now forced open the valve because the pressure in here can no longer keep that valve closed. So now blood literally flows through into the left ventricle. Passively, it shouldn't make any sound at all when it is doing that. So, let's just recap quite a lot of biology that some of you might not have done before. We've looked at the sequence of events. We've looked at how the heart contracts. We've identified where the P wave was within the cardiac cycle, QRS wave and T wave. We've linked that back to the ECG, but we've got another lesson on the ECGs. and we've talked about the sequence of valves opening and closing. So what do I need you to do for the assignment on this? I need you to talk me through a complete cardiac cycle. It doesn't need to be an essay. What it needs to be is a series of diagrams similar to the ones that I've shown you, where you are clearly putting in bullet points next to the diagram what is happening in the heart at that stage. And of interest, I am looking specifically, can you identify where we see the P wave, the QRS wave and the T wave? Can I clearly see that you understand why pressure is so important in either opening or closing valves? Can you, on your diagrams, really show me that the valves are either open or the valves are closed? And can you go through the sequence? That's what I'm looking for. As I said before, the PowerPoint is here to help you, okay? Everything that's important on each sequence is in bold and in red, okay? So use the material that I've given you to assist you. Is that okay for everybody? I think you deserve a cup of tea. Go and have a 10-minute break.